sir.
you keep distance between mic and mouth slightly. Okay,
Yeah.
sir.
Now it is okay. Yeah.
Yes, sir. Yes,
So
sir.
so this is what I told you. No, molecule initially ground state by absorbing light of definite wavelength move to higher excited state S2. Internal conversion. From internal conversion, emission of light in the form of fluorescence. Then there will be a vibrational transition. From this T1, it will come to again radiative transition by name phosphorescence. There is a possibility of energy transfer, that is called resonance energy transfer. Okay, right. So coming to the hardware component of the fluorescence spectrophotometer. Since I told you, no, you have to capture both emission light that is being emitted and also light that is used for excitation. So there will be two filters in addition to monochromator. Okay, then there will be a light source, there will be a monochromator. From the monochromator, the light will move to the beam splitter 45-degree angle. Then there will be excitation filter, a para filter. One is called excitation filter, the another one is called emission filter. So light that is impact on the sample chamber, the light that is being emitted, that has to be captured. Assume the light that is being emitted is a fluorescence. The light that is emitted, that has to be captured by the monochromator, again emission filter, which is followed by monochromator, and there will be a photomultiplier tube which will amplify the signal by the process called photoelectric effect. The detector also contains what is known as a photomultiplier tube. PMT refers to photomultiplier tube. Ultimately, depending on the light that is being emitted, depending on the fluorescence that is being coming out of the sample, there will be a chromatogram. Okay. As you can see here, we already discussed about the absorption spectrum of tryptophan and tyrosine. Both are aromatic amino acid. So the solid line represents the absorption spectrum of the tryptophan. The stipple line represents the fluorescence spectrum of the tryptophan. Similarly, panel B, solid line represents the absorption spectrum of the tyrosine. Stipple line represents the emission spectrum, that is fluorescence emission of the tyrosine. If you look at, I want you to look at these figures very closely. The absorption spectrum, that is rely on the excited wavelength of light. If you look at for tryptophan, it is almost 210, right? Do you follow? The absorption of tryptophan is 210, but look at the emission spectrum, it is in the range of 360. So you have to remember always, the emission wavelength is always higher than the excited wavelength. Okay? Do you follow? The emission wavelength is always higher than the excited wavelength. Why? Energy is initially, the excited wavelength is used to excite the electron from the ground state to a higher energy state. During this process, some amount of light energy is liberated in the form of non-radiative transmission. That means there will be a loss of energy. Loss of energy leads to the increase in the wavelength of light. Do you follow? So the energy is very low, the wavelength increases. That's what we have studied in the first session of my lecture. Lambda indirectly proportional to energy. Okay. If energy is lost during the process of de-excitation pathway, the wavelength that is being emitted will be in the higher wavelength range, not in the lower wavelength range. Okay. That's why the emission wavelength is always higher than the excited wavelength. That is very, very important component of the fluorescence spectroscopy. You should remember this always. Excited wavelength is always in the higher range compared to, emission wavelength is always in the higher range compared to excited wavelength. Okay, right. So the whole process of chemiluminescence depends on the fluorescence only. Okay, right. So this is one of the simplified diagram which shows the structural components of the spectrophlorimeter. Okay, so there will be a monochromator, there will be a sample cuvette, there will be two monochromators here, there will be two filters. One will absorb light that is being absorbed, that is being used for the excitation. The second one monochromator used to capture the light that is being emitted. The light that is being emitted in this sample is the fluorescence. The fluorescence has to be captured properly. Both has to be taken up by the detector, which is working on the principle of photoelectric effect. Okay, right. So I told you, in the given sample, the tryptophan fluorescence can be measured. Fluorescence emitted by tyrosine can be measured. Fluorescence emitted by phenylalanine can be measured. There is one generalized statement I wanted to make. Molecules which are having the aromatic ring, they are shown to have the property of fluorescence. They are shown to have the property of fluorescence. Okay. So as I told you, there are some biomolecules which are not capable of showing the property of fluorescence because they do not have any fluorophores. But you can make this non-fluorescent molecule into fluorescent molecules by adding fluorophores externally. So the chemicals which can be used to induce fluorescence in the non-fluorescent molecule, they are called extrinsic fluorophores. Extrinsic fluorophores. Fura 2 is very popular. Look at here, ANS is a very popular one. Fluorescein, cyber green, we call it as cyber green. Fura 2, dancyl chloride, all these are they considered to be external fluors. If you look at very closely the structure of all these extrinsic fluorophore molecules, they do have a benzene ring. Do you follow? Could you able to see this? All these extrinsic fluorophores, they do have a benzene ring. Hello? Students, can you hear me?
Yes,
Yes,
sir.
sir, you are
Yes,
audible.
sir.
Yes, sir.
Yes. This is one of the reason why tryptophan, tyrosine, and phenylalanine, they are capable of showing the fluorescence because they do have benzene ring in their structure. They are aromatic amino acid, right? So the extrinsic fluorophores, whatever available commercially in the market, they are rich in aromatic group. That's why they are considered to be the extrinsic fluors. So if you add these extrinsic fluorophores to the non-fluorescent molecule, you can easily study the structural changes of those biomolecules also. Okay, right. These are the widely used, commercially available, but widely used in protein chemistry. Okay, right. Look at this. Seems to be a very simple graph which shows the fluorescent measurements of the one of the amino acid residues. If you look at very carefully, if you take any protein, any enzymic protein, for example, if any protein let us take any enzymic protein, for example. Proteins, they do require some coenzymes or cofactor. Most of the proteins or enzymes, they do require some cofactor or coenzyme. It may bind to some metal ions. Okay, it will bind to some cations also, like calcium, magnesium, and manganese also. So what happens when the protein interacts with these biomolecules or ligands, it can induce some structural change. What we call it as conformational change. CONFOR, structural change. So protein structural change of the protein, the conformational change of the protein is the inevitable process in all the biochemical mechanism. So that can be studied by using fluorescence spectroscopy. So this cannot be studied by using the UV visible absorption spectroscopy. So the interaction of coenzyme or cofactor with a protein or enzyme can be studied by using the fluorescence spectroscopy. What happens normally, when a particular ligand or ion is binding to the protein, it will actually increase the fluorescence of the particular protein molecule. Generally, what happens? I told you about the tryptophan, tyrosine, and phenylalanine. If you take the structure of the protein, normally these aromatic amino acids, they are not present on the surface of the protein. They are trying to bury inside the protein because they are all mostly hydrophobic in nature. They want to move away from the water. Thermodynamically, what happens? These aromatic amino acids cannot be exposed to the outside of the external environment of the protein. Okay. So during the process of ligand binding or substrate binding, what will happen? The whatever tyrosine, tryptophan, phenylalanine buried inside the core of the protein, because of this conformational change, they are being exposed outside. So when these amino acids are exposed to the environment, what will happen? It can easily expose to the light of particular intensity, so that it will increase the fluorescence, emission of the fluorescence. So increase in the fluorescence is an indirect way of measuring whether the protein will undergo a structural change or not. By simply looking at the change in fluorescence, okay, emission, you can easily study the structural variation of the protein of interest. Okay, the proteins are amenable for structural change or conformational change by binding to coenzymes and cofactors. Okay, right. So this can be studied by using only fluorescence spectroscopy. Okay, what we are actually going to measure is the intrinsic fluorescence. We are not going to add any extrinsic force now, because we are just going to add some metal ions to the enzyme or protein that will induce structural change, that will expose the intrinsic fluorescence of the phenylalanine, tyrosine and tryptophan. Okay, that's why I use the term use of intrinsic fluorescence measurements for the determination of ligand binding to the protein or enzyme of interest. Similarly, if you are working with some enzyme, the interaction of enzyme with substrate and enzyme with inhibitor can be studied by using fluorescence spectrophotometer. Okay, you might be knowing about, there are different types of enzyme inhibitions: competitive inhibition, non-competitive inhibition, and also uncompetitive inhibition. Okay, so the interaction between enzyme with that of substrate, enzyme with that of the inhibitor can be studied by using the fluorescence spectrophotometer. Okay, right. Similarly, protein-protein interaction. Assume that you have two proteins. These two proteins are interacting together during the biological process. How you can study? By using the technique called FRET, fluorescence resonance energy transfer. The basic principle behind this fluorescence resonance energy transfer is nothing but a fluorescence spectroscopy. Okay, so by using the simple technique, again you can easily study whether the particular protein, two proteins are interacting together or not. That can be studied. I'll give you only one example. RUBP carboxylase is an enzyme, okay, which is capable of fixing atmospheric carbon dioxide during the phase 2 process of photosynthesis. LSU is synthesized within the chloroplast. Smaller subunit of this rubisco is synthesized from the cytosol. Both these subunits, the smaller subunit has to be transported from cytosol to the chloroplast. Within the chloroplast, these two subunits, larger subunit and smaller subunit, has to interact together. Then only it can fix atmospheric carbon dioxide efficiently, carbon fixation mechanism. Okay, so if you want to confirm whether LSU and SSU is joining together before it fixes atmospheric carbon dioxide, it literally means protein-protein interaction, right? This can be confirmed by using fluorescence spectrophotometer. Need not be always LSU and SSU of rubisco. Any protein-protein interaction can be studied by using the fluorescence spectrophotometer, provided both the protein should have a intrinsic fluorescence property. They should have amino acid residues of either tyrosine, tryptophan and phenylalanine in a at least a minimum number. Okay, if the number is not minimum, no, number of this tryptophan, tyrosine, phenylalanine is very, very low, the particular protein will emit only very weak fluorescence. Okay, generally what happens, all these aromatic amino acids are capable of showing fluorescent emission. The signal will be very strong, it is not very weak, except the DNA molecule. Look at this picture. Okay, don't worry about the technical details of the picture. So here the scientists wanted to try whether the calcium binding, whether the particular protein is able to bind calcium. If it binds to calcium, what are the structural changes the calcium is going to make in this particular protein? If you look at very carefully, they have taken an intact protein and they have added calcium. So in the presence of calcium, in the absence of calcium, they are measuring the fluorescence. Then what happened? They removed only C terminal of this protein and they have tested whether this protein now is capable of binding to calcium or not. Then they removed the N terminal of the protein, they keep only the C terminal, and now they wanted to test whether C terminal is capable of binding to calcium or not. If you look at very carefully, when they retain both N terminal and C terminal, in the presence of calcium, look at the signal, fluorescent signal, it is highly increased. Look at the signal, fluorescent signal in the absence of calcium, only by retaining the C terminal, no fluorescent signal at all. But in the absence of calcium, what happens? There is a very weak signal. But the presence of calcium induces the fluorescence property. That means the calcium binding induces a structural conformation of this particular protein. When they retain only N terminal, still there is a weak signal of fluorescence. But in the absence of calcium, there won't be any fluorescence at all. That means what? This protein is capable of binding to calcium. Calcium binding induces the structural conformation of this particular protein. Among the N terminal and C terminal, N terminal is very, very critical for the binding of calcium than the C terminal, because in the absence of C terminal, there won't be any signal at all. So in the absence of N terminal, there won't be any emission signal at all. So by simply using the fluorescence spectrophotometer, the interaction of calcium with the protein or any type of divalent cations, not only calcium, Mg2 plus, can also be tested by using the fluorescence spectrophotometer. Let me make it very simple. The structural conformational changes of the protein can be studied by using fluorescence spectrophotometer. Okay, so there is one technique by name, it is called tryptophan fluorescence. We call it as trip fluorescence. Trip fluorescence is one of the simple technique by which you can study whether the protein will undergo any conformational change or not in the presence and absence of any type of ligand, whether it is divalent cation or monovalent cation, anything can be tested. Okay, the same, instead of calcium, I can test with whether this protein is capable of binding to iron or not. That can be tested very easily. Okay, so in most cases, what happens? The fluorescence spectroscopy has a very wide application to study the protein-protein interactions. Okay,